Let's do the next example. So here I am flying Emily Killian for Peter Pan. The machine shown is a wheel and axle that operates with 95% efficiency. The wheel has a radius of 18 centimeters. The axle has a radius of 10 centimeters. A. What's the ideal mechanical advantage of the machine? B. What's the actual mechanical advantage of the machine? C. What weight can be lifted by a constant speed by a 20 Newton effort force? D. If that 20 Newton force acts through a distance of 3.5 meters, how far will the weight move? So let's solve this problem. What I want you to see is that for every turn of the wheel, the effort is going around the large circumference, whereas the resistance is going around the small circumference. So if you want to, you could say that the effort is equal to the circumference of the large wheel. That's the effort distance, whereas the resistance distance is the circumference of the small wheel. Well, if you take the ratio of those two things, there's going to be a 2 pi that's involved that'll divide out, and you end up with the radius of the wheels. So now if I put in the radius of the wheels, then I'll figure out what my ideal mechanical advantage is. I find that the ideal mechanical advantage is 1.8. Alright, well what about the actual mechanical advantage? They tell me that I have an efficiency of 95%. But that efficiency is the ratio of the actual mechanical advantage divided by the ideal mechanical advantage. And since I know what the ideal mechanical advantage is, then I can solve that for the actual mechanical advantage. I'm going to do that and put in the numbers. I get that the actual mechanical advantage is just over 1.7. Part C. What weight can be lifted at a constant speed by a 20 Newton effort force? Well, the forces are going to be related through the actual mechanical advantage. So I'm going to solve that actual mechanical advantage for the output force. Now you can see that I'm using the variables F and D sometimes instead of the numbers or the variables that your authors use like R and E. Forces I tend to like to call F's, but if you can keep those things straight, what's the output and what's the input, then hopefully you'll be able to think your way through these things. So using this system and an effort force of 20 newtons, then I could lift something that was just over 34 newtons. Part D. If the 20 Newton force acts through a distance of 3.5 meters, how far will the weight move? Well, I know what my ideal mechanical advantage is, and I know what my input distance is. It's 3.5 meters, so I can figure out what the output distance is going to be. Now my ideal mechanical advantage is 1.8, and since they tell me that my 20 Newton force acts through 3.5 meters, my input distance is going to be 3.5 meters. So using this system, if I pull 3.5 meters worth of rope around the big axle, then my weight is going to lift by just under 2 meters, 1.94 repeating meters. So let's review this lesson. We have defined the different simple machines and figured out what the input and output distances are. We've talked about ideal and actual mechanical advantage and efficiency, and we've used that to solve some numerical problems. So for now, that's it.